These are the notes for chapter 3.4, concavity test and the second derivative test. So we'll first focus on concavity test. Let's observe these two graphs. These two graphs, you can see the behavior from left to right. The graphs both are increasing with a positive slope. However, we see that their curvatures are a little bit different. And these functions we can say are both increasing with a positive slope. And what do we know about their derivatives? Okay, and that the rate of their slope, however, is changing. Okay, so here in this case, if we look at the slope of the tangent line, the slope is becoming more and more positive. It is moving towards the positive direction. Let's say this is a slope of 1/2, 1, 2, 3, 4. So it's moving in the positive direction. Here, even though the slope is positive, we see that from left to right, the slope of the tangent line is decreasing, and it's moving in the negative direction. So let's say this is a slope of 4, 3, 2, and we see the slope becoming more and more gradual, and it is moving in the negative direction. Okay. This graph represents where the slope is becoming more positive. We call that concave up. So concave up doesn't mean that the graph is going to be positive. It just means that the rate of change of that slope is moving in the positive direction. So in this case, this is a slope of maybe -3, -2, -1, 0, 1, 2, 3. So as we move from left to right, the slope of that tangent line is going towards a positive direction. When that happens, we have a graph that's concave up. Okay, if a graph is where the slope of the tangent line from left to right is becoming more and more negative, moving towards the negative direction, then we can say that the graph is concave down. Okay. So visually speaking, any part of the graph that resembles a parabola that opens up will be concave up. Any part of the graph that resembles a quadratic function or a parabola that opens down, we can say that graph is concave down. Okay. Some more because statements so that we can be very specific when we give our reasons. If f double prime is greater than 0, if the second derivative is positive, then f double prime, our function f prime is increasing, and therefore our function is concave up. Our f prime is increasing, meaning that the rate of change of the first derivative is moving in the positive direction. Okay. If f double prime is negative, then we know f prime is decreasing, meaning that the slope of the tangent line is moving towards the negative direction, and f of x is therefore concave down. A point of inflection, POI, occurs whenever f double prime changes signs. So this is where our function changes concavity. So that connection point between where the slope changes from concave up to concave down, or vice versa, from concave down to concave up. An example of this would be this graph here. This portion of the graph represents a parabola that opens down, so this is concave down. And then this portion of the graph is concave up, so that point where that interchange occurs is called the point of inflection. Right, the concavity test, which I call it the concavity test, this allows us to find the interval where the graph is concave up and concave down, as well as POI, point of inflection. So the way we do that is we're going to follow the same steps to find critical points as we did with first derivative. It's just that now we're using the second derivative function, and the results are going to mean something a little bit different. So we find the second derivative, set our second derivative equal to 0, which will then allow us to find the critical points. Again, critical points, you need to consider both the numerator and the denominator, depending on what the function looks like. If there's variables in the top and the bottom, we need to consider both. Okay. Once we find all the critical points, we put them all on the same sign line. And then we plug intervals into f double prime to determine concavity. So let's say we have 3 critical points, and in this region I chose a value to the left of the first critical point into the second derivative. In return, I get a positive. That means that this region of the graph will have concave up. And I use the parabola that opens up to indicate as a visual that the graph will resemble this shape. Graph is concave up. If I have a negative in the region, then I know that in this region my graph will resemble this, concave down. Positive, concave up, negative, concave down. Now wherever there's a change in concavity and that point exists, then we can say that point is point of inflection. So some because statements, we can say the graph is concave up in the interval from A to B because f double prime is positive. We can say the graph is concave down on the interval from A to B, endpoint to endpoint, critical point to critical point because f double prime is negative. And point of inflection occurs because or when f double prime changes signs. So in this case, these three critical points will all be points of inflection because there's all going to be change in signs here. Okay. Point of inflection may exist on the graph where f double prime does not exist. For instance, the sharp point. A point of inflection exists as long as the graph is continuous and f double prime changes concavity. There's a change in signs. So just because f double prime does not exist does not mean that it can't be a point of inflection. Just like with f prime, just because that we have a sharp point or where f prime doesn't exist doesn't mean that means we can't have a relative max or relative min at that point. So here's an example where there's a point of inflection where f double prime does not exist. Here there's a vertical tangent line, but you see that the graph changes from concave up to concave down. So here this resembles a graph, a parabola that opens up. This resembles a graph where a parabola opens down. That interchange, that point where where concavity changes is point of inflection. Right, let's look at example 1. Find the points of inflection for our function and find intervals where graph is concave up and concave down. So to find a point of inflection, we need to find the critical points for second derivative, and to find that we need to first go through f prime so that we can get to f double prime. So let's go through Powell rule. This negative 2x to the fifth becomes negative 10x to the fourth. 5/3 x cubed becomes 5x squared, so that will lead us to our f prime. From f prime, we need to go one step further down to get to f double prime. So go through Powell rule. Negative 10x to the fourth becomes negative 40x cubed. 5x squared becomes 10x. We set our second derivative equal to 0. To find our critical point, we factor out the negative 10x, and we're left with 4x squared minus 1. So we have three critical points. One is at 0. The other, 4x squared minus 1, is equal to 0. We got plus or minus 1/2. So we have three critical points. Next thing we do is we choose values in each interval, and we plug them into the second derivative function to check the signs. So here, if I plug negative 1 into the second derivative, I'll get a positive times a positive, which is positive. So I know this region is concave up. Here, if I choose negative 1/4, I will get a positive and a negative, so therefore concave down. If I can choose 1/4, positive 1/4, so I'll get a negative times a negative, which is a positive. And finally, if I choose 1 here, I'll get a negative and a negative, negative and a positive, which is negative. So f double prime is concave up. Our function is concave up on negative infinity to negative 1/2, and then also from 0 to 1/2 because f double prime is greater than 0. Our function is concave down because on this interval from negative 1/2 to 0, and then from 1/2 to 0 because f double prime is negative. Here, all these points exist on the graph, all these critical points exist on the graph, and there's a change in signs for each of them. So we can say point of inflection occurs at these x values, negative 1/2, 0, and 1/2, because the f double prime changes signs. Notice that we don't have to indicate where the sign changes from positive to negative or from negative to positive. We do have to do that if we have to indicate whether there's a relative max or relative min. But with point of inflection, there's not much distinction between concave up to concave down or from concave down to concave up. So as long as we state that f double prime changes signs, then this will be sufficient. Now, if you say from positive to negative or negative to positive, that would not be incorrect. But just to let you know. Also, these are physical points on the graph, so we need to, if we want to find the ordered pairs, we will plug -1/2, 0, and 1/2 back into the original function, and that'll give us the physical location of those y values. These physical points on the graph has to be plugged back into the original function.